Baby, I was talking the whole time. I don't know. All right, all right, all right. I was getting wrecked the last time I was playing. Getting wrecked the last time I was playing. All right. I know for a fact that too. All right. This is a very bad move. Oh no. What the hell did I do? This is this is resignation worthy. This is GG. I completely wrecked my position. Ah, this was bad. Alright, alright, alright. I already got up. Let's say. Uh, what am I doing? Come on. What the hell did I do? I mated this guy. Absolutely bonkers. I didn't know that I would meet this guy. Anyways, session 14 has started. 16:32. Absolutely strict timings. Strict timings. We know for a fact that 2 games takes this. So the last time, this case theory. All right. So we knew this. So this is the starting point where I can reach. Now, just this, I have to connect this with the fact that connect this with the fact that there is something like in electromagnetism, that we have that del cross B is equals to mu naught J plus mu naught epsilon naught del E by del t. I don't want to put the arrows again and again, just to say. Now, obviously, A and phi are our potentials. So, some coordinate system. So, I would say that this guy, the guy which I will say is named as coordinate system. I took so basically coordinate system. So what I so these B. So what is same? What is same? Ah. So I gave this guy B. I gave this guy. I gave this guy B. I gave this guy J, and I gave this guy an E, and it gives me something A and 5. Is it is this gauge theory? Have I Is this the relation? Now this is the question. Is this the relation? Or or B, J and E define for me an A and a phi, and I give this to this coordinate system, and they give me some value या फिर कह सकते हैं फंक्शन. It gives me some function for A, and it gives me some function for phi. Very interesting. So I should compare it with this. What remains the same in this? Obviously, what changes is the value of V in every. So the value of V changes at in every gauge, but the force remains the constant. So I know for a fact that force has remained the constant, and such. So changes of coordinate system, that is also true. So for example, I would have said that, okay, so I have established such a system in which it gives me V and it returns a V square value. So when I differentiate this, I take its grad, then the value of F will be something else. Obviously, because I have now squared the whole thing. Every point continuously has been squared. Has been squared. So if V is equal to X, then now V is equal to X square. And previously there would have been a constant force, and now the force is changing with respect to the X in this coordinate system. And a coordinate system is not only confined to this. There can be multitude of things that can be asked from this coordinate system, and multitude of things can be returned. Right. So that is also there. So what of these two is the truth? Certainly, there is the constancy of physical world. The physical world does not change with change of my coordinate system. That should not be the case. So in a sense, only those gauges should be allowed, only those coordinate systems should be allowed in which if nothing changes, then from switching to any of those coordinates, or any of those coordinate systems, any of those machines which return out something, those things should not change. So what it takes in is the same thing, but it gives me multiple a and phi values. That is the case. So this is wrong because there cannot be. So this would imply, actually, if this implies, actually this is wrong in a sense. Now understand, this is wrong. This is wrong because this would imply that there is a special frame, or there is special coordinate system that we know for a fact does not happen. That does not happen because of special relativity already has said this, that no frame, no coordinate system is special. It should not be the case. It should not be the case. If for this there is a special a and phi which I give, their returns are different a's and phi's, that first of all does not make sense, and that would necessitate a special frame which does not occur. With this implies that this formulation is probably the one, or a third one that I don't have the mental capacity to think of at this point of time, or the experience is lacking. So for the time being, I would say that there is physical values. So there are physical terms in a coordinate system or a gauge. And now this coordinate system is also known as a gauge. This coordinate system is also known as a gauge. Now he will tell me what a connection is. Now he will also tell me. So I have understood this. Yang-Mills gauge theory. What? No. This is not what he promised. No, this was promised by this guy. Since E and B control. So now, okay. If this understanding is then I will go back to Yang-Mills only. They said that this is there for every arbitrary function we may transform the potential by but still get the same electromagnetic field since E and B control the dynamics of charge part by Lorentz force. We write the same physics after this transformation. Indeed, this is a case of gauge transformation. So gauge transformation is obviously those that have some symmetry. That means that symmetry simply means that on the change of this baksa, nothing changes. Hence, this change of baksa is nothing, right? This is what it is. Alright, alright. Further. Indeed, this is the case in the manifestly so this is what he motivated last time, right? Oh my god. Oh my god! I cannot understand this. GG's. Topology घुसा Wow, what the hell? Bro, this is too involved. I am too involved in this, bro. This is not required. No way this should be required, man. This should not be required. Is that monopoly? How do you expect to learn this? This is not your thing to learn, man. I would tell you this much. This you do not require. I don't require this at all. This is too high level, man. This is too high level. This is too high level. You don't need this. You don't need this. This is unnecessary. I have fallen into a trap, basically. A second. If oh no, shit. This might not exist. I have to search for the notes of that guy. Definitely, I have to search for the notes. That would improve my chances to understand what needs to be understood. Because it is becoming very very difficult. It is becoming very very difficult, and it is not required for the difficulty does not need to be this high. You're already too deep. Obviously, who the hell is this guy? I don't understand. A second. Wait a minute. If if and only if I were to do this. Wait, I have to search something. Himanshu Gupta. Alright. If that is the case, then I will have to look for that. Himanshu Gupta physics notes, basically. How hard should it be? Himanshu Gupta physics notes. Ah, physics. Physics. Optics. Philosophy. No, not 2019, obviously. No, 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 no. Physics, UPSC notes 2016. 2016. Our singer. Session 14 has ended. I guess this is what I was looking for. This is what I was looking for. Oh, I don't know that. Maybe I could do this. Well, it is what it is, man. I would say it is what it is. It is what it is. He tried, but he could not. I just could not understand what he was doing. I did a super blunder, but he believed me. That was nice of him, I would say. Who the hell cares? Blunder is returned with a favor, you know. Now I am ouch. 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 Yes, I got it. That was neat, I would say. Shit! I got him, but I butchered it. So let's say there's a gauge theory. To simplify, in, to summarize and simplify form, the procedure for setting up a gauge theory. Global symmetry must be found. This global symmetry is converted to a local symmetry by changing the definition and coordinates and contains something equivalent to a charge. Now, what the fuck is this? Two changes. Here there is charge. There must be something to be seen. So let's say that there is something. Let us say that there is something. Let us say, let us say that there is something that is globally, when I change, the physics does not change. Let's say something is there. I found something, but the physics does not change when I do this. And this is not that abstract that I don't even know what this is. This is nothing but change of coordinate system. Change of coordinate system. Change of coordinate system. Even I will do it. I don't care. I don't care, bro. I don't care. I don't care. I will find something that will make me understand gauge theory, gauge theory, gauge theory. I will completely understand gauge theory at a level. Gauge theory for dummies, non-dummies, non-experts.
Hello, everyone. Welcome to the biggest ideas in the universe. I'm your host, Sean Carroll, and today's big idea is kind of a payoff. I know that in the last couple of videos, we did ideas that were heavily mathematical. We did a video on geometry and topology. Then we did a video on symmetries, which is, of course, based in physics. But what we talked about was the mathematical language in which we describe symmetries, the language of group theory. So today, we get the payoff. Today, we're going to show why.
Okay.
Hello, everyone. Welcome to the biggest ideas.
Hang on. There is some guy. Space, time, space, time, space, time. Okay, so there are little lectures. Speed, interaction. Right.
Hello,
Alright.
everyone. Welcome to the biggest
I'll give you
ideas in the
time.
universe. I'm your host, Sean Carroll. And last time when we talked about scale, we had the pleasurable experience of going back to the real, tangible world just a little bit, being a little bit more down to earth after several lectures on quantum field theory. We're going to get abstract again over this lecture and the next one, but it's in a slightly different direction. We're going to be thinking classically again. What we're going to be doing is laying some of the mathematical groundwork for the lectures to come. I keep saying lectures. The videos, the ideas to come. We have big ideas. They're going to require a tiny bit more mathematical sophistication, but it's more conceptual, less algebraic and equation-based, so I think it will be okay, but I'm going to be giving away some of the ideas that we physicists use all the time and we don't usually talk about in popular level treatments of the subject. So today we're going to be talking about geometry and topology. You will notice these are two different ideas and they're not really physics ideas. They're completely mathematical ideas. So of course they each are huge subjects which deserve videos of their own. They're not going to get them. I'm going to try to squeeze both of them into a single video, and I'm going to be concentrating specifically on very specific aspects of geometry and topology, ones that will be relevant to what we're going to be talking about coming up. So it's not going to be covering the whole field. So think about geometry and what do I mean? What I mean is non-Euclidean geometry. So to make sense of that, let me first talk about Euclidean geometry. This is the geometry that you learned in high school or wherever you learned it. Even if you didn't take any formal courses in it, you've heard about Euclidean geometry. It's the geometry of tabletops. It is sometimes literally called tabletop geometry. It's the geometry of flat planes and flat three-dimensional surfaces. So Euclidean geometry is things like if you take a triangle and you add up the angles inside, they add up to 180 degrees. Sometimes 180 degrees is called pi radians. Just a little math fact there. But we can use degrees. We're not going to try to be too snooty here. That's one fact about Euclidean geometry. Here's another fact, the parallel postulate, which is an interesting... has an interesting status, let's say, in Euclidean geometry. The parallel postulate says the same thing. Imagine you have two lines going off at right angles to a common line. So I'm thinking these two lines going horizontally across the page. The parallel postulate essentially says, there's different formulations of it, but essentially says that you continue these lines forever and they remain exactly parallel. They remain exactly the same distance apart from each other if they start going in the same direction and at right angles to each other, okay? This is, I think, the fifth of Euclid's postulates, and it's one that sort of seems more specific than the other ones. The other ones of Euclid's postulates, Euclid was a real person in ancient Greece who came up with this formalization of geometry. He had help, but we give him credit these days. And the other postulates are more or less self-evident, like, it's sort of what do you mean by a point and a line and things like that. Whereas this one, I don't know, seems a little optional. And there's been for a long time this idea that maybe we should be able to derive the parallel postulate from other postulates. And in fact, when I took geometry for the first time in junior high school, our teacher gave us an extra credit assignment of junior high school? No, high school, I guess. He said if you can prove the parallel postulate from Euclid's other postulates, or the other postulates that we had in the class, then he would give us extra credit. I was ignorant enough to actually try to do it, but I was not stupid enough to succeed in doing it, because you can succeed in doing it. That's the point. The point about the parallel postulate it is independent of the other axioms. That's why it's a good axiom. If it were provable from the other axioms, you could remove it from the list of axioms. And one of the reflections of the fact that it is removable is that you can contradict it. You can have other postulates that say other things, and that's the birth of non-Euclidean geometry. So Euclidean geometry, of course, works for triangles, works for straight lines, but it works for a whole bunch of things. I mean, there's a whole huge subject of Euclidean geometry about conic sections and inscribing circles within squares and calculating areas of things. I'm not going to be talking about any of that stuff. I want to dive right into what happens if we violate the parallel postulate, if we replace it with something else. So there are basically two choices if you want to violate the parallel postulate, right? Or if you want to replace it with something else. You might say that, well, maybe parallel lines generally focus on each other. If you start off with two parallel lines, that is to say lines that are both moving at right angles to some common line segment, maybe over space, as you extend them out, they come closer and closer and eventually cross. That is something that could happen. It does not happen in Euclidean geometry, but you could imagine it happening. You could also imagine diverging. You could imagine starting with two parallel lines, moving at right angles to a common segment, and as they move off, they get further and further away. Both completely standard, or completely plausible, in other words. And what you could do is you could actually invent a rule for how quickly they focus in on each other or how quickly they diverge. And interestingly, this was first done, I think in the 1800s, by Lobachevsky. No chance I'm going to spell Lobachevsky correctly, because I don't even think it's standardized. And Bolyai. These are two... Oops, I should be able to spell his name correctly. They invented what is now called hyperbolic geometry. They worked independently from each other. Two mathematicians I'm not even going to get their countries right. I just don't know the history of this stuff nearly as well as I know the history of physics. But Lobachevsky and Bolyai both said, well, okay, what if we, in effect they said this, again, I never read their papers, but in effect what they said is, what if we examine this possibility that the lines diverge rather than remaining parallel? And they developed a set of rules for what is now called hyperbolic geometry in parallel. You can, just like you can prove that the angles in a Euclidean geometry have the angles in a triangle in Euclidean geometry add up to 180 degrees. In hyperbolic hyperbolic geometry, a triangle sort of looks more like this because lines diverge. And you can prove that the angles inside are always less than 180 degrees. How much less depends exactly on the triangle and exactly how on the geometry, but it's consistently less than that. And this was interesting. It's not completely clear that Lobachevsky and Bolyai were the first to invent this. Gauss, Carl Friedrich Gauss, who was one of the greatest mathematicians of all time, he claimed to have done it first. Gauss apparently, he was one of the greatest mathematicians. He could also be a bit of a dick, apparently. He was very fond of talking to other mathematicians and being told by the others, oh, I have some great new result. And Gauss would say, oh yeah, I had that several years ago. I just decided it wasn't worth publishing. So he did that exactly to non-Euclidean geometry. And usually, I think he was right most of the time. Like he didn't publish that much, but he had a huge number of results. And so Gauss thought about this, Lobachevsky and Bolyai thought about this. And there is a story that you are sometimes told in the popular physics literature that goes something like Euclid invented Euclidean geometry, and then Lobachevsky and Bolyai invented non-Euclidean geometry, and that led right into general relativity, the curvature of space-time. So that's true, but it leaves out an enormous amount. And in fact, the specific work done by Lobachevsky and Bolyai in inventing hyperbolic geometry is not even specifically relevant. It's not very helpful, let's put it that way, to general relativity at all. It's far, far too specific. It's also like a little bit weird. In retrospect, it's a little bit weird because think about a surface on which you could actually use hyperbolic geometry. Like when I'm trying to explain non-Euclidean geometry, the most obvious thing in the world is to look at the surface of a sphere, okay? Here's a sphere. And you can take a little line segment being, for example, on the equator of the sphere, and you can shoot two parallel lines up, and guess what's going to happen? They're going to come together at the North Pole or the South Pole. So that's an example of this focusing kind of geometry, not this diverging kind of geometry. So this is, the spherical geometry is very visualizable, whereas if you actually want to get hyperbolic geometry, people say it's sort of saddle-shaped and things like that. So you can draw a saddle, and you can sort of put a point there and have two lines that are initially parallel, and they will diverge from each other. Da, 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 da. So a saddle shape, or a Pringle, if you're a fan of the American potato chips, saddle or Pringle-shaped geometries are hyperbolic. But there's something nicer about the sphere than the saddle, which is I can embed the entire two-dimensional sphere perfectly accurately inside our good old three-dimensional space. Whereas this saddle is indeed curved in the sense of Lobachevsky and Bolyai, but it's not constant curvature. They were actually examining the very, very specific case where the curvature was exactly the same in all senses and in all places in your geometry. That's true for the sphere. The sphere is completely symmetric. Its amount of curvature is the same everywhere. There exists a hypothetical two-dimensional geometry, a negatively curved hyperbolic geometry, for which that's true in the diverging sense. But the saddle does not quite fit that category, that criterion of being constant curvature everywhere in the form in which it's embedded in our three-dimensional space. So that's a long-winded way of saying it's actually hard to visualize absolutely symmetric, constant curvature, hyperbolic geometries compared to spherical geometries. But nevertheless, historically, that's what they did. They invented the negatively curved. This is, just to make this clear, this is called negatively curved geometry. Sphere would be positively curved. And Euclidean would be flat. Zero curvature, okay? Euclidean geometry. And all these are possible. So it's perfectly allowed to invent hyperbolic geometry first as an alternative Euclidean geometry, but it's just weird to me that they didn't invent spherical geometry first. However, like I'm hinting at, none of these is what we want in some sense. I mean, these are all a starting point, but a very, very tiny starting point. We need to work a lot harder to get what you actually need for physics out of this. So it was Gauss who first sort of figured out how to do something more general. What I mean by more general is, let's imagine that instead of generalizing a flat Euclidean plane, 2 dimensions, instead of generalizing it to a two-dimensional sphere or a two-dimensional saddle, we just let it be any old thing, okay? We just let it be some wildly diverged thing. There's sort of all lumps here and whatever. It has curvature of arbitrary amounts in arbitrary directions everywhere throughout it, okay? That's really what you want. In general relativity, because we're going to get to general relativity eventually, and that says that space-time is curved. And if you ask yourself, well, is it positively curved or negatively curved? Well, in some places it's positively curved, in other places it's negatively curved. And in fact, you need a lot more information than just positive or negative to tell me how curved it is. That's what we're going to develop right here. And Gauss was the one who made the first steps toward this. He was examining surfaces, two-dimensional surfaces, and he figured out different ways to characterize the curvature at a surface. So for example, here's one way that you could do it. Take on a sphere, take the North Pole, and consider circles, lines of latitude, okay, around the sphere. Well, they would have, around the North Pole. So they would have a circumference, just like in this flat geometry, circles would have a circumference, okay. There's a radius and a circumference. And in flat geometries, the circumference is simply 2 pi times the radius, 2 pi r. That is how far you have to go around the circle. If you look at this spherical geometry over here, you notice that the circles are sort of moving toward each other a little bit compared to what they would be in the flat geometry. So if you try to calculate the circumference of a circle in the spherical geometry as a function of the radius, you find that consistently the circumference is, oops, that's exactly what I didn't want to write. The circumference is less than 2 pi r. Every single time for a circle. Whereas on this saddle over here, if I were to draw some circles and I would compare it, it's hard to see on the thing I drew because it's hard to draw a negatively curved surface. But here the circumference is consistently greater than 2 pi r, where r is the radius of the circle. So that's one example of what I mean by characterizing quantitatively the curvature of a surface. Once you say that, once you say, well, okay, the circumference of a circle of fixed radius is not 2 pi r, it's something else, maybe what I can do is I can say, well, how different is it? How less is it? Of course, it's infinitesimally less, but then I can use calculus to sort of differentiate, take the derivative of how the circumference is changing as a function of the radius, and I could characterize that separately at every point. It's not once and for all a feature of the geometry, but at every point in space, I can draw a little circle, or if in three-dimensional space, a little sphere, and I can compare how the area of the sphere or the circumference of the circle would depend on the radius. Compare that to what it would in flat space.
Obviously. Because the R is much greater. The length will be much
curved geometry, and I can do that separately at every point. So I get a number at every point, which is how much I'm deviating from completely flat Euclidean geometry, and that number could be positive or negative. So that's an example of how you could characterize curvature locally. And it's clear just from sort of examples you could imagine in your head that a curved surface could be very curved some places, not so curved other places. So that's really what you want. And Gauss figured out how to do this for this case of two-dimensional surfaces. But then he noticed something, because he was one of the greatest mathematicians of all time. He noticed something. He noticed that there are ways of characterizing the curvature that don't make use of the fact that this two-dimensional curvy thing is embedded in flat three-dimensional space. So think about there's sort of extrinsic, not just from sort of deviating from on the radius in geometry, but at every point in space, I can draw a little circle, or if in three-dimensional space, a little sphere, and I can compare how the area of the sphere or the circumference of the circle would depend on the radius. Compare that to what it would in flat space to my curved geometry, and I can do that separately at every point. So I get a number at every point, which is how much I'm deviating from completely flat Euclidean geometry, and that number could be positive or negative. So that's an example of how you could characterize curvature locally. And it's clear just from sort of examples you could imagine in your head that a curved surface could be very curved some places, not so curved other places. So that's really what you want. And Gauss figured out how to do this for this case of two-dimensional surfaces. But then he noticed something, because he was one of the greatest mathematicians of all time. He noticed something. He noticed that there are ways of characterizing the curvature that don't make use of the fact that this two-dimensional curvy thing is embedded in flat three-dimensional space. So think about, there's sort of extrinsic, sorry, my brain was thinking something else, so I wrote badly. Extrinsic versus intrinsic curvature. Extrinsic is just the curvature you get from looking at it from the outside, whereas the intrinsic curvature is what you get from looking at the inside. So if you have, let's say, this circle, and this is literally supposed to be a circle on a plane, okay, so it's a two-dimensional circle embedded in, sorry, a one-dimensional circle embedded in this two-dimensional plane, versus, let's say, this blobby thing, okay? So you would say, look, well, this one is curved, but kind of smooth, not that curved. This one is also curved, but it's curved in a different way everywhere. So what Gauss says is you're thinking extrinsically. You're thinking about how the thing looks from the point of view of the outside. But what I want to do, Gauss, is I want to think about what if I were a little person living in that surface, living on the surface of the circle. It's hard to imagine that, but I can imagine being a little person living on the surface of this two-dimensional plane, or I could imagine that three-dimensional space itself has curvature, and I could be a person living in that, right? So in that case, what Gauss shows is that this circle here and this circle-like thing that is kind of wobbly have exactly the same curvature. In fact, technically they have zero curvature, as we'll see in a second. But the point is that you're moving the circle in the place where it's living, but you're not changing its intrinsic geometry. So what Gauss figured out is what you really want to be able to do is two things. You want to characterize the geometry intrinsically to where you are, And number two, you want to be able to characterize all the different ways in which the surface or the volume or whatever you're in is curved. This fact that circles or spheres change their area or circumference differently as a function of the radius is one way, but there could be lots of different ways, lots of different aspects of curvature. And Gauss did not quite finish this project. He didn't quite tackle it all the way, but he had a very talented student named Bernard Riemann. Riemann was a brilliant mathematician who went on to do many great things. Riemann also died when he was 39 years old. So when you look at all of the things that Riemann accomplished, keep in mind that he didn't reach the age of 40 before he did those things. So Riemann apparently, he needed to write some thesis, some dissertation to get some job in Germany, and he went to Gauss and said, okay, here are the different topics that I'm thinking about. What's your advice? Which one should I do? And this is the story I'm told anyway. Again, don't know the history very well, but Gauss said, oh yes, this one, the foundations of geometry. Do that one. And apparently Riemann thought that was the most boring one that could be done, but he did it, and he invented what we now call Riemannian geometry. Pretty cool. And so what I want to do is give you some of the fundamental basic concepts of Riemannian geometry. Riemannian geometry is the answer to the question if I have not just a two-dimensional surface, but any space of any number of dimensions, so three-dimensional space, four-dimensional space-time, whatever you want, and I curve it not just uniformly everywhere, but I curve it arbitrarily at any point, okay, in different ways, at different locations in space, and as we now know, in time. How do I completely characterize the amount of curvature? How do I know how curved it is? How do I describe that mathematically? So he figured out how to do this. And basically, I think that the thing to think about are straight lines. This is my favorite way of getting into Riemannian geometry. What do you mean by a straight line, right? Well, we have one notion of a straight line, is that the straight line is the shortest distance between 2 points, okay? That's perfectly good. So version 1 is shortest distance. And you can do that. You can generalize that Euclidean notion of I have 2 points, I take the shortest distance path. So in Euclidean space, I take 2 points, and I notice that this shortest distance path is straight. Other ones that are not straight will always have longer distance if I measure the distance along them. And I can do that equally well in a curved space. So what we call great circles on a sphere are lines that are as straight as they can possibly be. If I take a point that is here at the North Pole, and then take another point that is at the equator, and I connect them, there is this is part of a great circle. If I go all the way around, a great circle is just something that is like the equator, but it's not necessarily at the middle. It's anywhere oriented around the sphere. And this is the spherical generalization of the idea of a straight line. You can show that these great circles are the shortest distance between those 2 points. And then you can show other things, like if I do another point there, then the shortest distance here is along the equator. If I connect these, there's another shortest distance curve, another line of longitude in this case, and then I can add up the angles inside the triangle, and they're always greater than 180 degrees because it's a spherical geometry. I can do all that stuff, okay? So that is one version of what you mean by a straight line. How would you generalize this to a completely arbitrary geometry? Well, you remember when we did the principle of least action, we had this idea that there was some quantity, the action, that you could get by integrating over an entire path for a particle or for some more complicated physical system. And then the real path, the real trajectory that obeys the equations of motion, minimizes that action. So you can do exactly the same thing for the length of a curve. But what you need is a way to calculate the length, okay? So that's what Riemann figured out how to do. He invented something called the metric. The metric basically is the infinitesimal length. It's not quite the infinitesimal length. Again, this is one of those times when all of the experts in the audience are cringing a little bit, but just lighten up, guys. It is a way of calculating if I give you an arbitrary curve, and I want to take a little bit of it. Okay, there's a tiny little segment because I'm thinking like calculus, right? This is all what we call differential geometry. It's all calculus-based reasoning where you take infinitesimal things, figure out what's going on there, and then add them together along some finite-sized thing to get the final answer. So there's something that called Pythagoras' theorem, right? That you can take these, if you had ordinary Euclidean geometry, you would say that A, B, C, if A is the length of one of the ways you can go, B is the perpendicular way, and C is the hypotenuse, then A squared plus B squared equals C squared. So basically the metric is a generalization. Pythagoras' theorem, C squared equals A squared plus B squared. It says that C squared does not necessarily need to equal A squared plus B squared, but equals some function of A and B. In fact, it's some quadratic function. So it could be something times A squared plus something times B squared plus something times A times B. Okay, so 2 factors of A and B in general. So in fact, let's write it that way. So the infinitesimal length of this tiny little curve segment here equals something, call it alpha times A squared plus beta times B squared plus gamma times A times B. Okay, So the numbers, alpha, beta, and gamma, are telling you how to calculate the length of an infinitesimal curve in an arbitrarily curved geometry. That's what the metric does. And then you can just add them all together along the curve. It's like a little odometer, right? You're pushing this little odometer and it's measuring your path length as you go. And these numbers, alpha, beta, gamma, that tell you how to convert little coordinates, which are what A and B are, into physical lengths, which is what C is, they could change from place to place in the manifold, as we call this space of all different points. A manifold, a space, whatever you want to call it, some curved object in geometry will in general have a metric that is different at every point in the manifold. I got to call it a manifold, sorry, that's what it is. So the manifold is this space that is curved. Whatever it is, how many ever dimensions. It could be, by the way, by is curved, I mean could potentially have curvature. Maybe it's flat, who knows? But it is the space that we will be talking about when we characterize what the curvature is, okay? The curvature of a manifold. So space-time is a manifold, a four-dimensional manifold. Space that we live in is a three-dimensional manifold. The tabletop is a two-dimensional manifold. The sphere is a two-dimensional manifold, and so on, okay? So the metric is, guess what? It's a field on the manifold. It's a kind of field that exists at every point, and at every point it answers the question, if I have a little straight line segment, how long is it? That's what the metric is. And I can add that up to get the length of a finite-sized curve. And that's a wonderful way to do it. That's a wonderful way to sort of generalize what you mean by a straight line. A straight line is the shortest distance path between 2 points. You can generalize that to arbitrarily curved surfaces. Riemann tells you how to do that. But there's another way of talking about a straight line. A straight line can be thought of as keep walking in the same direction. So if I'm literally on a flat plane and I'm just walking, right? If I were to wander around in different directions, what I would mean is that the momentum or the velocity or the little vector that points towards the direction.
Infinite decimal length. Huh? This makes sense. Here we have carried down.
I'm moving keeps changing around, okay? Like I move around and my velocity changes. That vector is sort of wobbling back and forth as I'm moving. Whereas in a straight line, I just keep walking in the same direction as the vector is pointing, as the velocity, as I have already been moving. If there's something that says, here's the direction I was moving in infinitesimally long ago, I will keep moving in that direction now. That is what I'm going to do. So in flat space, this idea, you are in flat space, you have a point here, you are initially walking in that direction, and you just keep walking in that direction until you reach some other point, you're going to end up moving in a straight line, okay? That's what you're going to do. So that's an equally good alternative definition of what you mean by a straight line. Just keep walking in the same direction. That also works in these more complicated examples. If I start walking north from the North Pole, and from the equator, and I just keep walking in the same direction, I will end up doing a great circle path until I reach the North Pole. Everything I just said goes through. So Riemann was smart enough, and again, I'm not even sure that it was Riemann who did this. He sort of got the answer, but I'm not quite sure what his reasoning was, so I shouldn't attribute it to him. But what we realize is that there's some notion of what do you mean by keep walking in the same direction, okay? You have this vector, and you're saying move in the direction of the vector. The vector is the thing that is pointing in the direction I have been moving in, and what I'm saying is keep moving in that direction. So what I need is a way to sort of carry vectors along with me as I travel. And if I have that, then I don't need to just do it with the vector that is pointing in that direction. I mean, imagine that I'm walking around in space carrying a gyroscope, okay? Just good old ordinary Euclidean space. If I have a gyroscope, and you might know if you sort of suspend a gyroscope so that you're not forcing it in some direction, you can just carry it around, and the gyroscope, if it's spinning, will keep pointing in the same direction. So this is a notion called parallel transport of vectors. It's just a way of saying you have some vectors, keep them parallel to what they were as you carry them around. Keep vectors parallel to what they were. And this notion that you keep walking in the same direction is, in the lingo of general relativity, you parallel transport your velocity vector. So you have a velocity vector, and you also have this notion of how to move things, keeping them parallel to each other. And a straight line is one in which, if you have a vector pointing in the direction you're moving, you keep parallel transporting that. The vector that is your actual velocity matches what you get by doing your original velocity and just keeping it parallel. This is what math is all about. Let me just sort of pause to emphasize this. I just said what a straight line was in two different ways, and we all know what a straight line is. Like, it's this perfectly obvious thing. So why are we complicating it? Like, that's like the worst definition of a straight line you've ever heard. Invent a notion of keeping vectors parallel as you move, and then compare a parallel transported vector.
Like, exactly. Oh, exactly. This is what I was thinking, man. Bro. This is what I was thinking. What are we doing, bro? This is straight. This is straight. This is straight. Is it not straight? It's straight. Straight is with this. Straight is which is made by a scale. What is this? What is this? Is curved. What is this? Fucking. I. Oh no. Property damage. Bruh. That has to be time. Bro, that has to be time. Yes. Now 15th session is over. 15th session is over. So basically, we will be doing. This is great. It helps me understand what the hell Iceberg's book just crammed it so hard. I cannot understand. It just has left so much that oh you don't need it, but I needed to understand what is the problem. To just expand things. When I have the patience, I will read that shit. Damn. This is Euclidean space, no curve. Maybe, who knows? Oh, maybe the night does not have a curve, you know? You understand what I'm saying? Mandem. Mandems. Mandems. What the hell? What was that? What was that? Let's say this. And well, all right. Let's say this. What about this now? Oh, this is nice. I got something for you. He also resigned. Bro, the moves were too good. The moves were too good. Oh, I had this. Who cares? Oh, what the hell is that? Come on, man. Fuck off. Hey, this was so bad. Damn. Oh my god, that was so bad. Misclick after misclick. Hey, Bhagwan. Alright. This was just so bad. You want to win? Try. Try. I will see. Let's see. Let's see. Let's see. You wanted to flag me, bro. I flagged you back. Okay, so this is how many sessions? 1, 2, 3, 4 sessions. We're done. Oh my god. Man. Ah. I guess we will meet later. I'm done. I'm done for the day. Uh, we'll meet later. Maybe 7, 7:30. I don't know.